What is the difference between integral and differential Maxwell's equations? Imagine trying to understand how electric and magnetic fields behave across space and time. You might think of it as looking at a map of a city or zooming in on a single street. Both views are important, but they serve different purposes. That's what Maxwell's equations help us do. They give us two ways to look at the same phenomena. Now, let's explore what makes the integral and differential forms of these equations unique and how they fit into electrical engineering. The integral form of Maxwell's equations relates the fields over a whole surface or loop. Think of it as measuring the total amount of electric flux passing through a surface or the total magnetic circulation around a loop. For example, Gauss's law and integral form tells us that the total electric flux through a closed surface equals the charge enclosed divided by the permittivity of free space. This means if you know the total flux, you can find out how much charge is inside. Similarly, Faraday's law and integral form relates the electromotive force around a loop to how quickly the magnetic flux through that loop is changing. These forms are very practical because they connect directly to measurements you can make with instruments like voltmeters and flux meters. On the other hand, the differential form looks at the fields at a specific point in space. It uses calculus operators like divergence and curl to describe how the fields change from one tiny spot to the next. For example, the differential form of Gauss's law states that the divergence of the electric displacement field at a point equals the charge density there. This gives us a detailed, local picture of how charges influence the electric field right at that spot. Differential equations are especially useful for detailed computer simulations and analyzing complex geometries where the fields vary rapidly or inside materials. Now, how are these two forms connected? They are actually two sides of the same coin. Using mathematical tools called vector calculus theorems, Gauss's divergence theorem and Stokes' theorem, you can convert an integral equation into a differential one, and vice versa. Gauss's divergence theorem turns a surface integral into a volume integral, linking the total flux to local divergence. Stokes' theorem turns a line integral into a surface integral, connecting circulation to curl. This mathematical relationship ensures that both forms describe the same physics, just from different perspectives. In practical electrical engineering, the integral form is often used when working with circuits, antennas, or boundary conditions where total flux or circulation matters. Engineers might measure the total electric flux through a surface or the total magnetic flux around a loop. The differential form is more common when designing devices like waveguides or analyzing electromagnetic compatibility, where understanding how fields change at every point is essential. Numerical methods, such as the finite element method or finite difference time domain simulations relying on the differential form to predict how fields behave inside complex structures. To sum it up, the integral Maxwell's equations give us a broad view of how fields behave over regions and relate directly to measurable quantities. The differential equations zoom in on the local behavior, providing detailed information about how fields change from point to point. Both are vital tools in electrical engineering, helping us understand, design, and analyze electromagnetic systems from the smallest components to large-scale networks.